In this first example, we're given a double integral over some region, and we need to make a change of variables to write it as an iterated integral. This region E that we're integrating over is a parallelogram, and I'm giving us the 4 vertices of the parallelogram. And I'm actually going to give you 2 different solutions to this problem, just so that you can see a couple different ways of generating an appropriate change of variables. First up, let me draw a picture of this region so that we can get an idea of what kind of thing we're integrating over. We have a corner at 0, 0. We have a corner at 3, 1, which maybe I'll draw here. We have a corner at 1, 2, which I guess would look like this. And then the other corner is at 4, 3, which means somewhere over here. And there's our parallelogram. Our goal in a problem like this is to figure out a map from a rectangle in the UV plane, which gets sent to this parallelogram under that map. Now, the 2 different solutions that I'll present are 2 different ways to approach finding this, but ultimately we want to figure out some rectangle over here and some transformation where the rectangle will get mapped to the parallelogram. What I'll do is I'll think about these lines that are generated by the parallelogram. As always, a good way to think about a region in a plane is by its boundary curves. So what I'll do is I'll just find the equations for all of these boundary curves. For example, this line right here passes through the origin and it looks like it has a slope of 2 because I move over 1 and go up 2, which tells me that the equation of this line is y equals 2x. Likewise, this line also has slope 2. Now we could use point slope format, for example, with this point here to get the equation of the line. This would be y minus the y value is 1. This should equal the slope, which also has to be 2 because it's parallel to this other line, times x minus the x value. And then if we do some simplification, it looks like we would get y equals 2x. This is minus 6 plus 1 is going to be minus 5. Let's do the same with the other lines. This line has a slope 1/3, so I know that its equation will be y equals 1/3 x. And then a similar process to find this line equation. It also has slope 1/3, and it passes through the point 1, 2. So we would get y minus 2 equals 1/3 times x minus 1. And after some simplification, this would be y equals 1/3 x minus 1/3 plus 2 is plus 5/3. So there are the 4 boundary curves that define this region. So I could summarize this by saying that the region E that we care about is defined by the following relationships. And actually what I'm going to do is I'm going to take each of these equations and do some simplification where I squish all of the variables onto one side. For example, in this equation here, if I subtract the y over to the right-hand side, I would get 2x minus y equals 0. Here, after some similar simplification, I could get 2x minus y equals 5. So what do those 2 lines tell me? They tell me on the one hand, 2x minus y on one side is bounded by 0. That came from this equation. And then on the other side is bounded by 5. I get an inequality like that. I'll do the same thing with these 2 equations. Just because fractions are annoying, I could multiply through by 3, and then I could subtract the x over. That would give me terms that look like 3y minus x. This equation becomes 3y minus x equals 0. And then this equation becomes 3y minus x equals 5. So these 4 boundary equations here, which cut out the original region we care about, give us a set of 4 inequalities. The reason why this is really useful is because we can easily see a nice variable substitution. If I were to call this thing 2x minus y u, and this v, for example, the resulting region in the UV plane would be described by a rectangle. So let's do that. I'll let u equal 2x minus y. and I'll let v equal 3y minus x. There's our change of variables. By this set of inequalities, what this tells us is that the corresponding region in the UV plane is a rectangle. Okay, and so we've got a nice variable transformation, and we know the corresponding region in the UV plane. The main thing to remember about changing variables in an integral is that when we start off with an integral in the xy world, as we are here, with this multivariable variable change, what do? Well, we have to change the bounds, which is just to say, redescribe the region in the UV plane. We've already done that. We have to figure out how to rewrite the original function in terms of u and v. So this will look a little confusing when I write it. I wouldn't worry about too much. This is just saying write x in terms of u and v, and write y in terms of u and v. Then to change the differentials, this is where the Jacobian comes in. So what we need to do is we need to multiply in here by the absolute value of the Jacobian of this g function, which goes from the UV world to the XY world. And then I multiply that by dA in the UV plane. And we say, okay, great, we've got our change of variables. All we need to do now is just compute the Jacobian, plug in for x and y, and then we go from there. We have a couple issues, really, which can be summarized by the fact that this variable transformation does not define g. G is a map from the UV world to the XY world. We have something going the other direction right now. This variable change, as we've written it down, describes u as a function of x and y, and v as a function of x and y. So this variable change here is actually the inverse of g. This is really important. It's important for a couple reasons, but generally we need to write x in terms of u and v and y in terms of u and v, which is opposite from what we have here. And we also need the Jacobian of g when we change the integral. So one way that we could fix this issue is we could just figure out what g is. We have g inverse. To figure out g, we just solve for x and y. We could, for example, do this by starting with the second equation here, solving for x. This would give us x is, 3y minus v, to which we could plug that into the first equation. And then in this one, we can solve for y. It looks like we have 6y minus y is 5y. That'll equal u, and then on this side, we have a minus 2v. So when I move that over, I'll get u plus 2v. There we've successfully solved for y, and we can use that to determine x. In particular, just use this equation, plug in our expression for y, and x will pop out. And after some simplification, it looks like x is 3/5 u plus 3 times 2/5 v is 6/5 v minus v would be 1/5 v. In other words, what we've shown is that g as a function of u and v is the vector valued function where the first component is right here, the second component is right here. Now that we have g, we can easily compute the Jacobian that we need, and we can also easily solve for x and y in terms of u and v. That's what we've done right here. Plug everything in, and then we'll have successfully changed this to an iterated integral in the UV plane. Let's compute the Jacobian first. So remember that to compute the Jacobian in this case, we want to take the determinant of the matrix, where in the top left corner I have the partial of x with respect to u. Over a spot I compute the partial of x with respect to v, and I do the same thing with y in the second row. While these partial derivatives are easy to compute, the partial of x with respect to u is just going to be 3/5. Likewise, the partial with respect to v will be 1/5. Partial of y with respect to u will be 1/5. And then with respect to v, it'll be 2/5. The determinant of this matrix is going to be 3/5 times 2/5 minus 1/5 times 1/5. So that comes out to 6/25 is 3/5 times 2/5 minus 1/25, which is 5/25, which is 1/5. Okay, and with that, we're pretty much set to use this change of variables formula to turn our original integral, which was x plus y over this parallelogram, into a uv integral over this rectangle. So to finish it off, the double integral over e that we care about, x plus y dA, what do we get? Our bounds, both u and v are bounded by 0 and 5. So I'll get the integral from 0 to 5 here, 0 to 5. F was x plus y. Up here in the top right corner, we have x and y solved in terms of u and v. So x plus y, if I do some algebra in my head, 3/5 plus 1/5 is 4/5. So I'll get a 4/5 u. Plus, then if I add the v's together when I do x plus y, we'll get 3/5 v. Then I need to multiply by the Jacobian here. The Jacobian that we computed was 1/5. So from the Jacobian, I pick up an extra factor of 1/5, and then I've got du dv. And that would do it. If you wanted to, you could actually evaluate the integral. I don't care about doing that. I just wanted to change variables appropriately. This is one way to do it. Like I said, I'll give you a second solution too, which really only differs in how we decide how to pick this variable change. So what is this second method? I will say that this is a little more linear algebra based. If you've taken linear algebra before, this might make a lot of sense. If you haven't taken linear algebra before, I wouldn't worry about it too much. So this is sort of just an optional bonus solution. So here's our region E again. And just like before, what we're looking for is a map G from the UV world to the XY world, which is sufficiently nice. And usually for a linear change of variables like this, we're going to be looking for a map such that the pre-image of this red parallelogram is a rectangle. In the previous solution, the way we did this was by looking at these boundary lines, using that algebraic data to determine an appropriate change of variables. A different, more linear algebraic technique that we can do is we can decide from the beginning what we want our rectangle to look like in the UV world. For example, suppose I want to cook up a map so that the corresponding region in the UV plane is the square spanned by the two standard unit vectors. Geometrically, I want to cook up a map so that this vector gets mapped to this side, and likewise I want this vector to get mapped to this side. Since I'm doing a linear change of variables, I can specify the whole map by just specifying what happens on a basis. Since G will be a linear change of variables, it'll be given by matrix multiplication. Now, how do I specify a linear transformation which maps this vector to this vector and this vector to this vector? Well, the images that I'm looking for, those will just be the columns of my corresponding matrix. So the first column I'll make 3, 1. The second column I'll make 1, 2. So each of these columns correspond to sides of the parallelogram. And then since we're not in a linear algebra class, we can multiply this out to get this in a more familiar looking form. I would get 3u plus v. And then in the second component, I would get u plus 2v. And there you go. There's our change of variables. X is 3u plus v. Y is u plus 2v. One of the benefits of this method is that we actually literally have the map G. In the previous solution, we used the data over here to cook up a map going this direction. Then we had to do some algebra to figure out the map in the direction that we wanted. With this tactic, we write this down from the beginning. So by construction, G inverse of E, in other words, this is the purple region. We cooked this transformation up so that it's exactly the unit square. The next thing we need is the Jacobian. Again, we already have the G that we need, so we can just compute the relevant Jacobian, which is going to be the determinant of, in this case, the partial of x with respect to u will be 3. Partial of x with respect to v will be 1. And then when I compute the y partials, I'll get 1 and 2. And not really surprising that that's literally the same matrix as this. This happens precisely because this is a linear change of variables. This determinant is going to be 6 minus 1, which is 5. The original double integral that we started off with this change of variables, which should be said is a different change of variables than in our first solution. And that's okay. There's not one correct change of variables here. They're similar up to a scaling factor of 1/5, but they are different. So with this new change of variables, the bounds in the UV region are 0 to 1, 0 to 1, coming from here. The function is x plus y with this change of variables. X plus y is going to be 4u, let's see, plus 3v. The relevant Jacobian is 5, then du dv, and that would do it. Like I said, this is not the same iterated integral as in the first solution because we had a different change of variables, but their values should be the same as long as I did all of this correctly. If you don't believe me or if you're really bored, you can just compute this second integral that we computed, compute the first one, and you should get the same number. The differences are being picked up in the region that we integrated over, and that's taken into account with the Jacobian. Anyway, 2 different ways to come up with an appropriate change of variables to integrate over a parallelogram. Okay, in this next example, we have a nonlinear change of variables map. So the integral that we ultimately want to evaluate is the integral of xy over some region E. That region E is in the first quadrant. It's bounded by y equals x, y equals 3x, xy equals 1, and xy equals 3. And we'll use the change of variables map given by this function here. Okay, so as usual, let me start off by sketching a picture of the region that we care about. So on the one hand, we have 2 lines, y equals x, y equals 3x. Easy enough to sketch. Then on the other hand, these 2 equations, we could think about solving for y here. For example, you would get something like y equals 1 over x. And in the second equation, you'd get y equals 3 over x. What do those look like? Well, y equals 1 over x will look something like that. Y equals 3 over x will just be the same rough shape shifted up. And so here's a very rough picture of the region that we care about in the xy world. Now the map G eats a point in the UV world and spits out a point in the XY world. And one of the first steps here is going to be to figure out exactly what the pre-image of this region is over here. In other words, what shape in the UV world do I feed into G to spit out this region E? In general, a good way to think about this is to look at the components of G. These are x and y respectively. I'll take this information and plug it into the inequalities that were given in terms of x and y to try to translate them into inequalities in terms of u and v. So in particular, x is u over v and y is v. Let's think about, for example, what this second inequality tells us. The fact that xy is bounded between 1 and 3, what does this tell me? Well, x times y is u over v times v, which is just u. And okay, so we've got a nice interval for u values. I'll do the same thing with this other inequality to see what it spits out. So the inequality x less than y less than 3x, what does this become? X is u over v, y is v, and 3x would be 3u over v. Now, because we're interested in an interval for v, what I'll do is I'll just roughly solve for v. I could do that by multiplying through by v here. And then after taking square roots, I have an interval of v values. Now, a couple remarks. One of them is that v depends on u. In other words, what this is showing us is that the region over here in the UV world is not a rectangle. That's fine. The other small thing to point out is when we take a square root, technically you always need to consider whether we're dealing with a positive square root or negative square root. But based on the picture here, I know that y is always positive. Well, y is v, so when I take a square root, v needs to always be positive. So that's why when I took square roots, I just considered the positive ones. But okay, so now we have a description of the corresponding region in the UV world. Let me sketch a picture of this really quick. This inequality came from the two orange lines. So u equals 1 and u equals 3 would look something like this. And the second inequality came from the two red lines, roughly. So we have v equals the square root of u, which maybe looks like that. Then we have v equals the square root of 3u, which is going to look something like this. So here's our region. Next, we'll need the Jacobian of g. So as usual, this will be the determinant of the matrix of first partial derivatives of g. So I'll take dx du in this corner, dx dv in this corner, dy du in this corner, and dy dv in the lower right corner. So the derivative of x with respect to u, pretty straightforward. This will be 1 over v. Derivative of x with respect to v, this is like u times v to the negative 1. So by the power rule, I'll get a negative u over v squared. Then in the second row, the derivative of y with respect to u is 0. The derivative of y with respect to v is 1. So the determinant here is going to be 1 over v times 1, which is 1 over v, minus 0. Okay, so we have the changed region, we have the Jacobian. Now we're all set to use our change of variables formula to evaluate the original integral. So the original integral that we care about is the integral of x times y over this region. By the change of variables, we'll get the integral over the UV region. Now, looking at our bounds, u has constant bounds, v has variable bounds. In other words, what we're picking up here is that this region in the UV world is vertically simple. It's v simple. So I would want to integrate with respect to v first. The lower bound will be root u, the upper bound will be root 3u, and then the bounds for u are 1 to 3. Then the function is x times y. Recall that x was u over v and y was v. So this will turn into u over v times v. And then the Jacobian here is 1 over v. Now we always put the absolute value of the Jacobian in the integral, but like we talked about before, v is positive. Then I've got dv, du. These v's cancel out, so ultimately we're left with the integral from 1 to 3, the integral from root u to root 3u of u over v. Now it's just a matter of evaluating this integral. The antiderivative with respect to v is going to be log v. I'll evaluate those at my upper and lower bounds. Now when I plug in root 3u and root u for v, the u I can factor out will get log of root 3u minus log of root u du. Then using log rules, I can actually combine these, right? This will be log of root 3u over root u. And then this simplifies very nicely, actually. The root u's cancel out, so we get u times log of root 3. Antiderivative here is going to be u squared over 2 times that log of root 3. Evaluated at 3 and 1. plug these in, and then we are done. 3 squared is 9, so I have 9 halves, minus 1 half is 8 halves, so I get 4 here. And then just for fun, to simplify this a little nicer, log of root 3 is the same thing as 1 half times log of 3 by log rules. So the 1 half times 4, I could write this as 2 log 3. And up to silly computational mistakes, that will do it.